Hey everyone, today we're going to talk about scale diagrams. I'm going to go over kind of the definitions, how to determine it, and we're going to go over a few examples. So for scale diagrams, what they are is they're a drawing in which measurements are proportionally reduced or enlarged from actual measurements. A scale diagram is similar to the original. What we want to talk about with scale diagrams is that we're looking at something and I'm taking an image or an object and I'm scaling it up or down by some factor. And so when we scale things up or down, what we're looking at is that we need to make sure that every single measurement, so its length, its width, its height, everything like that, is enlarged or reduced at a proportional rate. So it's being done at the same rate no matter which measurement we're looking at. What this relates to is what's called scale factor, a number created from the ratio of any two corresponding measurements of two similar objects or shapes. It can be written as a fraction, as a decimal, or a percent. We tend to use the variable k to represent scale factor. So a few things that we need to know about k is that k has to be a number that is greater than 0, and then there's kind of three different things that we're going to be looking at. If I notice that k is a number that is between 0 and 1, then what that means is that the diagram has been reduced from its original size, so it's scaling down. If k is greater than 1, then the diagram has been enlarged from its original size, so we're scaling it up. If k is equal to 1, then the diagram has stayed the same size, so we haven't reduced it or enlarged it, it's just staying the exact same. Let's go over a few examples of what this may look like. So these two triangles are similar. Determine the scale factor and find the missing side lengths. Just as a reminder of what similar means. What similar means when it comes to triangles is that all side lengths have been made that are proportional to each other. So all side lengths are proportional. And then all angles are the same as well. So they have stayed the same measurement. All right, so looking at the two triangles here, what we can see is that they are similar and that when we're talking about the angles being the same, we would want the corresponding angles to be the same. So it would mean that this angle here is similar to that angle here. This one down at the bottom would be similar to that one again, and then that they're equal to each other. So that's kind of what I mean by similar. What we're looking at is that if this is my original triangle on the left and then it's been enlarged to the triangle on the right, what we want to think about is what can we do with scale factor, and how we're going to come up with a scale factor is by looking at the proportions. So in both of these triangles, I know this side and these sides are corresponding to each other. So when I look for the k value, what I can do is divide 9 centimeters from the one triangle and divide it by the other side in the larger triangle. When I divide these two, what I get as a decimal is 0.4, which of course as a fraction is 2/5, and then of course as a percent is 40%. Remember that we can represent the k value as a decimal, a fraction, or a percent, and that's kind of one of them. What if I put it the other way? Let's say that I'm going to call this k2. If I had gone 22.5 centimeters and divided by 9 centimeters, what I would get here as a k value is 2.5, which as a fraction is 5/2, and then as a percent is 250%. So just by using these two sides, what we can kind of see is that there's these two different k values that I can talk about. And what we want to know is kind of what's the difference from one to the other. So when we divided 9 by 22.5, we get a decimal of 0.4 or 40%. What that means is that if I was to start with the larger triangle and reduce its size, it would bring me to the smaller triangle. The opposite way is for when we went 22.5 and we divided by 9, and we get a percent of 250%. What that means is that we're starting with the smaller triangle and we're increasing its size by 250%, and we're getting the large triangle. So when you're representing the k value, what's important is that you know which one are you going to end from, because that percentage and that decimal is going to affect how you may do your calculations to solve for missing sides or anything like that. So let's start with solving for g. So if I have g here, and then let's say I have this corresponding side, which is 14. If I start with 14 and I'm going to the smaller triangle, then what I'd kind of want to start maybe looking at is the k value that I calculated the first time. So here, what I can do is go 14 centimeters. I need to reduce this size to 40% of its original. So I'm going to multiply by the decimal of 0.4. And this is going to give me my g value. When I multiply these together, I get 5.6 centimeters is equal to G. And so what that means is that 5.6 centimeters is 40% of 14 centimeters. And so we have reduced this size up to into 40%. All right, now let's find our other missing side length. So here we have 5 centimeters and it's turning into n. So we're starting with a smaller triangle and we're enlarging it to the larger one. The reason I like having both these k values is that then I can always do this as multiplication. So we're going to start with 5 centimeters and I need to multiply by the k value, which as a decimal is 2.5. And this is going to give me n. When I multiply those together, I get 12.5 centimeters is equal to n. And now I have my side length there. Let's try a few other examples of solving with scale factor. An architect needs to draw up a blueprint for a home they are building. Their client would like a rectangular master bedroom with dimensions of 18 feet by 22 feet. The architect will construct the blueprint using a scale of 1/4 inch to 1 foot. Determine the dimensions of the master bedroom on the blueprint. All right, first what I want to do is figure out what is my scale factor. So if I have, again, let's kind of just go over and highlight those important key pieces from the question. Their client would like a rectangular master bedroom and you want it to be this size, 18 feet by 22. Well, the architect will have to come up with some type of blueprint and it needs to be to scale so that someone can see on the blueprint, kind of, starting to visualize what this is going to look like. So the scale that they're going to have is that every foot in the bedroom is going to be represented by 1/4 inch on the blueprint. So we need to figure out what the k value is. Well, let's start with k is equal to. I'm going to compare this as a fraction, and I'm going to turn this into a decimal as well. So we have 1/4 inch, and we're dividing that by 1 foot. When we look at a k value, it's nice if we can have things being the same unit. So instead of writing this as 1 foot, I'm going to convert that into 12 inches. Now what that allows me to do is that when I divide inches by inches, my units cancel, and what's nice is that now my k value is just a number without units. So when I divide these and I get this as a fraction, actually let's start with a decimal. When I divide these, I get 0.0208, which as a percent is 2.08%. And again, those dots are representing that I have some numbers after that. But what's nice is if I turn this into a fraction, what I get is 1/48. And so now this is my k value. Now that we have a k value, we can use this to figure out, well, what would the size of the bedroom be on the blueprint? Well, what we have here above is that we had the length and the width of the bedroom in real life. What we have as a scale factor is that it's going to be reduced to 1/48th of that size. So let's start with 18 feet. What we can do is multiply it by my scale factor of 1/48. And what this is going to do is tell me what the new size is. What here I'm going to get is 0.375 feet. If we wanted to have our answer in inches, we can multiply this by 12 because there are 12 inches in 1 foot. And then what we're going to get here is 4.5 inches. Let's do that same thing for the other dimension. So the other dimension is 22 feet. I'm going to multiply by my scale factor. And what I'm going to get this time is 0.4583 repeating feet. And again, that kind of 0.3 repeating isn't a really nice number. So let's turn that into inches. So 0.4583 repeating multiplied by 12. We'll turn this into inches. And what I'm going to get here is exactly 5.5 inches. Let's try another example. You were looking at a bacteria under a microscope that has a scale of 65. The magnified image of the bacteria you are looking at has a length of 0.75 centimeters. How long is the actual bacteria to the nearest thousandth of a centimeter? Okay, so what we have is that it's going to enlarge it by a scale of 65. So what we are seeing when I look into this microscope is I see something that has a length of 0.75 centimeters. That, of course, is not the real length of that bacteria. That is just what has been magnified for me. So we have a k value in this case of 65. And what we want to do is use that k value to figure out what's the real length of this bacteria. So I'm going to use my k value as a ratio this time, or as a fraction. So what that means is that when I see 65 centimeters on the microscope, like if I could actually see that distance, that would represent 1 centimeter in real life. And of course, 65 over 1 is the same as 65, and those units would cancel. So I'm still keeping the k value the same. But now what I'm leaving this open to is setting up another fraction on the other side and opening it up to cross multiplication. So 65 centimeters in, I guess, the microscope would represent 1 centimeter in real life. And so now we've kind of set up our numerator and denominator. So what I have is that what I see in the microscope is 0.75 centimeters. And so what I can do now is cross multiply and divide, and that's going to tell me what is the real length of that bacteria. So we're going to go 1 multiplied by 0.75, and we're going to divide by 65 centimeters. So x in this case will just be 0.75 divided by my k value. Let's plug that in. What we're going to get here is 0.011538, and we want to round it to the nearest thousandth, which means to 3 decimal places. So in this case, what my final answer will be is 0.012, and of course that's going to be in centimeters. I hope this video helps you with scale factor. Please let me know if you have any questions. Have a great day.